Hello everyone, I'm Dr. Q. Welcome to my channel. We have discussed the one-shot simultaneous move game. Let's switch to the setting of repeated games. There are infinitely repeated games and finitely repeated games. An infinitely repeated game is a game that is played over and over again forever without end, and in which players receive payoffs during each play of the game. Please recall the value of time. Future payoffs must be appropriately discounted in current decisions. And please be reminded that when a firm earns the same profit, pi, in each period over an infinite time horizon, the present value of the firm is equal to the profit multiplies 1 plus the interest rate and divided by the interest rate. As players now engage in repeated games, they care about the payoff in future. They will adjust their current strategy to make sure that their long-term value is maximized. Alternatively, they care about their reputation. Players or firms can communicate and collude. Therefore, even though the Nash equilibrium to the one-shot simultaneous move pricing game is low, when this game is repeated infinitely, it is possible for firms to collude without fear of being cheated on using trigger strategies. What is the meaning of a trigger strategy? It is a strategy that is contingent on the past play of a game and in which some particular past action triggers a different action by a player. For example, Target and Walmart agree on selling an electronic product at $50. This is a high price. By charging this high price together, both can get profit of $10 as a payoff. They will keep doing so until one of them cheats and triggers the price war. And everyone goes back to low price. Low price, which is the Nash equilibrium for one-shot game. How does one player know the other is cheating? There are many ways, such as website price. But what if the cheater offers some secret coupon or deal without letting everyone know? They use the consumers as whistleblower by offering the price matching scheme. For example, some consumers come to Walmart saying that Target offers the identical product $10 cheaper. Walmart will apologize and give $10 back to the consumers. Walmart matches prices to keep the consumers. Meanwhile, it is notified by the consumers that Target is cheating. Target broke their pact of collusion. Now Walmart revenge by charging a lower price as well. When will the firm choose to cheat? When will they not? Well, the player will compare the payoff of cheating against the payoffs of not cheating for now and the endless number of games in future. Suppose a one-shot game is infinitely repeated and the interest rate is I. Further, suppose the cooperative one-shot payoff to player is pi cooperative, which is $10 over here. Then the maximum one-shot payoff if player cheats on the collusive outcome is pi cheat. Here it is $50. The one-shot Nash equilibrium payoff is pi non-cooperative, pi subscription n. Here it is 0. If the numerator, the difference between profit of cheating and profit of cooperation, over the denominator, which is the difference between profit of cooperation and profit of not cooperation, if this ratio is smaller or equal to the inverse of interest rate, then the cooperative or collusive outcome can be sustained in the infinitely repeated game with the following trigger strategy. Here, we plug the corresponding payoffs into the formula. We got this. And the interest rate is supposed to be smaller or equal to 0.25 for the collusion to sustain in this context. So, what are the factors that affect collusion in pricing games? So, the sustaining collusion via trigger strategies is easier when firms know who their rivals are, who they're competing against, so they know whom to punish if needed. And the firms need to know who their rivals' consumers are, so they can effectively steal those customers with lower prices once the rivals cheat. And third, when their rivals deviate, they need to know that when their rivals deviate, so they know when to begin their punishment. And lastly, firms need to know all of those to be effectively and successfully punish rival. And they have the capability of doing so. Here are some other factors affecting collusion in pricing games. The first is the number of firms in the market. It is important to decide how many monitors there are. There are like n multiply n minus 1. So if there were 5 firms, each firm monitor the other 4, then there will be 5 multiplied 4, 20 monitors. The more firms, the more costly it is to monitor or collude. The second is firm size. It's easier to monitor. It's easier for the large firm to monitor the small firm. And third one is history of the market. We have a tacit collusion. What they used to do was convention. Last one is punishment mechanisms. If it's a single price for all customers, it is more expensive to punish than multiple pricing levels because they must change lower price to its own customers for all of those consumers. If it's different prices are quoted to different customers, a firm can punish its rival by charging the rival out customers a lower price. Infinitely repeated games rationale can be applied to product quality control. Firms want to build reputation to stay in the game infinitely. If interest rate is low, they choose to produce high quality. But what if there are some low quality products out of honest error? And firms can solve the problem by issuing warranties. Now we discussed one-shot and infinitely repeated simultaneous games. Let's think about the setting in between, the finitely repeated games. Well, the outcome of the finitely repeated games or limited number of repeated games essentially depends on whether the players know when the game will end or not. If they don't know when the game will end, they act like infinitely repeated game. Suppose the probability that the game will end after a given play is a theta, where theta in between 0 and 1. An uncertain in final period mirrors the analysis of infinitely repeated game. Again, the profit for cheating is 50. The profit for being cooperative, given there is a theta probability that the game ends next, is equal to $10 divided by theta. If profit of cheat is smaller or equal to profit of cooperation, then the players have no incentive to cheat, and the collusion will sustain. Firms will play the game like the infinitely repeated game using trigger strategy. Here we have cheat payoff of 50, cooperative payoff of $10 divided by theta. To solve this problem, theta must be no bigger than zero point 0.2. The chance of the game ends next is smaller or equal to zero point 0.2. Here's a practice. Please pause and try. Alright, here's the answer. So this is the profit of cheating, which is $20. And the profit of cooperation is 10 divided by zero point 0.1 is 100. And 20 is smaller than 100. The firm has no incentive to cheat. Firms collude by using trigger strategy. They will keep charging high. They will keep using the strategy of don't advertise until the rival cheat. Now, if firms know when the game will end, they act like one-shot simultaneous move games. When this game is repeated some known finite number of times and there is only one Nash equilibrium, then collusion cannot work. The only equilibrium is the single-shot simultaneous move Nash equilibrium. In a game above, both firms charge low prices. For example, if the games are played in 2 times and both players know that, so when they know that they're going to cheat and charge low price in the second time, then when they play the first time, they know that they will be cheating on next round. Then they have incentive to go ahead, cheat, and charge low price in first time. In fact, collusion can never work even if the game is played for 3 times, 4 times, or even 1,000 times, provided the firms know precisely when the game will end. The key reason firms cannot collude in a finitely repeated non-end point version of the game in this setting is that eventually a point will come when both players are certain there's no tomorrow. At that point, any promises to cooperate made during previous periods will be broken because there's no way a player can be punished in tomorrow for having broken the promises. Effectively, a player has an incentive to break a promise in the second to the last period, since there's no effective punishment during the last period. Because all the players know this is effectively there's effectively no tomorrow in the third period from the last. This type of backward unraveling continues until the players realize no effective punishment can be used during any period. The players will charge low prices in every period. Here are some applications of the end of a period problem. The first one is resignation and quits. When a worker announces that he's going to quit, say tomorrow, then the benefit of shirking on the last day exceeds the cost of being caught. What should the manager do? Well, if it legally permits, the manager has incentive to go ahead and fire the worker once the worker says he's going to quit. But should the manager do so? Probably not, because then the worker probably will wait until the last minute to announce that he's going to quit and he's still going to shirk. The manager won't solve the end of the period problem, but instead will be surprised by the resignation and have not enough time to find a replacement. The better solution is to be able to extend the reward beyond the termination, such as writing recommendation letters, etc. Another example is the snake oil salesman who moved from town to town, selling bottles of magic medicine that turns out that is a worthless substance. Buyers cannot do anything about it because the salesman is not there anymore. Similarly, you don't want to buy any expensive watch from a sidewalk vendor at a place of interest when traveling because when you buy some inferior merchandise, it's more costly to go back to doing anything. For punishment to work, there must be some way to link the past, present, and future as it relates to the seller. Alright, that's all I have for this video. I'll see you in the next one.